Welcome to Wyon Air Academy's and Swedvac's webinar on indoor climate and school performance of children. My name is John Woolett and I work for Wyon Air Academy.
My name is Veronica Eid and I'm the Managing Director of Swedvac. Did you know that by increasing the temperature in the classroom from 20 degrees Celsius to 30, you will decrease the performance of the children's work for about 30%? This means by increasing temperature only 10 degrees Celsius, you will get less work from the children, about 35%. Did you also know that with natural ventilation, 47% of classrooms in Swedish schools would have the CO2 above about 1,000 ppm?
Now, these may sound to you as just made-up figures or very big generalizations, but I promise you they are not. Our speaker today has spent the whole of his working career in researching the connection between indoor climate and performance, not only in school children but also in adults. For today's presentation, he will show you the results and back up those figures that we gave you just now with the amount of research and the way that he set out the hypothesis and then gone through the experimentation to get to those results that you just heard, and more. So with no further ado, I would like to welcome David Peter Wyon to the stage to join us here. Thank you.
Good morning, my name's David Wyon and I work with the Danish Technical University, the Technical University of Denmark in Copenhagen. We've been asked to present our research in the context of the Wyon Air Academy, and today I'm going to summarize a series of experiments which have been done over the last 5 to 10 years, some of them as much as 30 years ago. Oh, wait a minute, nearly 50 years ago. But that will emerge as we go on. This lecture reports the findings of a series of field intervention experiments that was carried out in schools in Denmark and Sweden on behalf of ASHRAE. For those of you who never heard of ASHRAE, it is the American Society of Heating and Ventilating Engineers. And they support a surprising amount of research everywhere in the world because their contracts are put out to bid. And we, DTU, were awarded the research contract in open competition with bidders from the United States, Europe, Australia and the Far East. The project that I'm going to begin by describing was known as ASHRAE 1257. This is the title of the final report of ASHRAE 1257, the effects of temperature, outdoor air supply and airborne particles on children in school classrooms. My co-author was Paul Wargocki, who I've worked with over the last 20 years, from the time when he was a postdoc to now when he is a distinguished researcher known all over the world. He's the president of ISIAC and the deputy director of the International Center for Indoor Environment and Energy at DTU. The main objective of ASHRAE 1257 was to determine whether improving air quality and ensuring that classrooms don't become warm can improve the performance of schoolwork by children. These are the two problems that teachers face, at least in temperate regions. It can get too hot when the sun comes through the window and the ventilation is not properly dimensioned. Similarly, throughout the winter, it may be too cold to open the windows or too windy, so the carbon dioxide content increases to the point where it passes the statutory limit of 1,000 parts per million that most countries adhere to. And we wanted to see what effect that had, because there are still plenty of people who don't believe that this has more than a small effect, 1 or 2% perhaps, which children should easily be able to compensate for, since adults believe that they can. In this experiment, we passively recorded window opening behavior. Unlike a laboratory experiment where everything is determined, we allowed these children and teachers to open and close the windows as they like. We don't have windows in climate chambers, so that wouldn't have been possible if we'd done these experiments in our laboratories. But we did them in the field in order to maintain a high level of reality. The methods that we used were to modify the indoor air quality by increasing the outdoor air supply rate from an existing mechanical ventilation system. In other words, we chose the school because it did have mechanical ventilation. The air temperature was reduced in hot weather by installing and operating what are called split cooling units. That means that they don't blow in cold outdoor air, they pump in cold Freon and use that to cool the air that's already in the room. So it doesn't affect the air quality, it just cools the air. And the heat is rejected in condenser units on the roof outside. The school didn't have these units, so we installed them for the purposes of the experiment. One of the reasons they agreed to take part was that we gave them the equipment and left it in place. It's cheaper to do that than to take it away. The window opening behavior was recorded simply as all windows closed or one or more open. And door opening was also recorded automatically. The school was in Denmark, on the island of Zealand, where Copenhagen is situated. Half the population of Denmark live in that area. Actually live within the bounds of Greater Copenhagen. And it's a big city, but the school was about 15, 20 kilometers outside the center, so it had very good outdoor air. It's on the shores of the Öresund Strait, which is international water linking the Baltic Sea to the North Sea. And our laboratories are situated halfway out towards the school, so it was convenient for us to get, for our PhD students to get there and back. This is an aerial view of the school. It was an elementary school with no indoor environmental quality problems, no reported problems. As you'll see, they did have a problem, but they didn't know about it. There were south-facing facades, so the classrooms did get hot in summer. It was mechanically ventilated, and energy conservation measures were in place, and there was the problem. Somebody sometime in the past had decided that the cheapest and simplest way to save energy was to reduce ventilation. Many of you will recognize that argument. It's very tempting to save a lot of energy by simply reducing the ventilation. That can be done with a piece of cardboard at the intake, or in a more sophisticated way by reducing the fan speed. And they had balanced ventilation so that much less than the engineers who built the school had intended was actually getting to the classrooms. This is a plan of the selected classrooms. You can see that we have a choice of identical classrooms. Could have been built for the purposes of the sort of experiment we wanted to do. This is a three-dimensional drawing of the classrooms. They were high ceiling height. That normally helps because the warm used air goes to the top. But it also helps to let in more sun. And of course the architect's idea was that sunlight is good because people like sunlight. They feel more alert when they see shadows and sun. But the problem is that sunlight is also a bearer of heat, a great deal of heat. And that meant that these classrooms got fairly warm in summertime. And if they hadn't had mechanical ventilation, they would have got even warmer. This is the view from inside. You can see there's a lot of glass on the south side of the classroom, but it's a well-designed classroom with good lighting and good daylighting, and plenty of volume for the limited number of children, 20-25, that they generally have in such classes. So our interventions took place in three different ways. We modified the ventilation system. We installed split cooling, which you can see on the wall there, discreetly, blowing the air across in front of the windows. And we installed electrostatic air cleaners of a new type. They looked like cupboards. They were cupboards, but inside they had a large sheet of paper that was printed with conducting ink, and that paper was maintained at 16,000 volts. The air of the room was drawn in at the bottom and blown out through the top, so it passed close to this sheet of paper, and as it came in, it was ionized. Small charged particles charges were added to the air so that they sat on the different particles of dust, and the dust was therefore deposited very quickly onto this paper. The point of making a deposition plate in paper is that you can easily throw it out and replace it. The problem with most electrostatic air cleaners is that it's very difficult and expensive to clean metal, non-disposable deposition plate, so it doesn't get done as often as it should be done. But these, as you will see from our measurements, these electrostatic air cleaners really did work. They removed the particles, and we wanted to see in this experiment, well, does that do any good? Do the children work better when we're removing the dust from the air? Because that would be a cheap alternative to bringing in more air to dilute the dust concentration. If we could just remove the dust particles, and if they were the problem, which we don't know, then, which we didn't know at the time, then that would solve the problem in a very energy efficient way. Similarly, split cooling just cools the air, as I said. It doesn't involve bringing in outside air, which has to be heated or cooled to the classroom temperature. So you get what you put in. You get the number of degrees of cooling that you pay for. And you don't have to also heat outside air coming in. In the ventilation system, we've just rebalanced it so that a whole lot more air went to one classroom than the other in pairs. Split cooling was installed and either operated or idled in summer. Those were the two conditions. We were either cooling it or we weren't. And remember that in both cases, the teacher and the children were able to open and close the windows as they saw fit, and we were simply passively recording what they did. The electrostatic air cleaners, I haven't mentioned that they were silent. If you put your ear to the door of the cupboard, you could just hear the fans running, and we made sure that they were running in both conditions. All we did was switch off the ionizer and the electrostatic charge on the deposition plates. So children are fairly curious, and they are not stupid. And if we had been less careful, they might have determined which condition they were in, and in this case they couldn't. I didn't say, I'm going back now one slide, I didn't say that the fans in these split cooling units ran all the time in both conditions. All that stopped or started in the two conditions was the flow of freon from the condensers outside. So that, again, the children were not able to determine if we were cooling the air, except by, of course, feeling the air. But they couldn't decide which condition we thought we were imposing. And the same in the air cleaning department. We don't have sensors for dust content in the air until it gets really bad and starts bothering our eyes. We cannot tell how many particles there are in the air. So I really believe that this condition was truly blind, and it was double blind in the sense that although we knew which conditions we were creating, the teachers and the children did not know. So the teacher was running the experiment, if you like, because we were never present. We were down in the cellar making sure that everything was working. The children never saw researchers in white coats. They didn't see anybody holding a stopwatch. They just came to school, went through their lessons with their teacher, and in that way we took a great deal of trouble to make sure that they at least believed everything was as normal. The pupils were 4th to 6th grade, 10 to 12-year-old children. And altogether, we involved over 300 pupils, and each one of them was exposed at least twice, some of them 4 times, in each particular experiment. That means that we can eliminate one of the main sources of variance, of variability, in terms of the performance of children and their, what they say, whether they feel it's too hot or too cold. If you compare a randomly selected child with another, you need a very large number, much more than 300, to be able to achieve the same kind of power that we did with these experiments. But if you remove individual variation by comparing each child with themselves under 2 different conditions, then even fairly small effects become more visible, effects that would have been hidden in the noise of inter-individual variation. I like working with 10 to 12-year-olds. I must have worked with tens of thousands of them over my 50-year research career. They are old enough to be able to do quite sophisticated work. They can read, in other words, and they can do simple mathematics. They are naive to the extent that they will do what the teacher says. If we work with children older than 12, then we start getting problems where they deliberately sabotage the experiments, and we have to take much more trouble to ensure that this doesn't happen. Again, then when we go to adults who are doing a job as we've done most of our work has been on adults, then they do their work in a responsible way, and they have a responsible attitude and do not sabotage our experiments. But it would be fairly easy for a gang of 16-year-olds to decide that they would all work very well on one day and very badly on another, just simply to increase the variance of our experiments, and we wouldn't get anywhere like that. Children in the age of 10 to 12 don't do that. The physical measurements that we made were divided into two sorts. One, measurements we made continuously, discreetly, but continuously, and one where we needed much more equipment, and we brought that in when the classrooms were empty. The continuous measurements with the pupils present were carbon dioxide, which was sampled continuously and measured, air temperature, the relative humidity, and the window opening state recorders. Really, we should measure these factors in every classroom continuously, and we should probably display them to the teacher because they are important for the progress of the work, as you'll see when I've finished. We then, from these measurements, we measured the effective outdoor air supply rate in litres per second per person. And this was estimated from the rate at which the CO2 level increased when a known number of children entered the classroom. From the teacher's logbook, we knew how many children had been present in each class or in each session. We could, from our own measurements, see how quickly the CO2 increased. And that is if we know how much CO2 each child produces, that tells us how much the effective ventilation rate is. And that includes not only the air that is being blown in from the mechanical ventilation, which we know about, we can measure that in other ways in the plant room, fall of pressure across a obstruction in the duct, for example. But also air that blows in through the windows as a function of the wind, direction and speed, and even through the doors. Even the air that seeps through cracks in the facade, if there are any. Any simpler way of measuring the effective ventilation rate will miss these extra contributions, which can be quite substantial, especially when we're working at very low levels of outdoor air supply rate. We also measured the children's perceptions and symptoms. Perceptions are what they think of the classroom conditions, and their symptoms are how they feel in various ways. So I've exemplified some of these scales that we use. They're called visual analog scales. I've used them with children down to the age of 8, and after a simple session introducing them to a teacher by a teacher with examples, even 8-year-old children are able to use these scales. For example, at the top, we ask them, is it too cold or too warm, or somewhere in between? You can see that the mark, the red transverse mark, in this case has been placed somewhere near the middle. Then, is it too drafty or too still? Is it humid or too dry? The air is poor, the air is fresh, it's too dark, it's too bright, too noisy, and so on. Now, that isn't a measurement. It's an estimate made by a particular child. It doesn't mean anything in itself, but we treat it as a measurement. We measure how many millimeters it is from the left-hand end, and that's our figure. It's at the ordinal level of measurement. In other words, the further it is to the right, the warmer the child thinks it is. And remember, we are comparing only each child with itself, not randomly selected children with each other. So if they mark further to the right in condition B, then we are justified in assuming that condition B feels warmer than condition A. That's what an ordinal level of measurement means, especially since the further they mark to the right, then the bigger the difference. Now, the symptoms are estimated in the same way. We ask them if their nose is blocked or they can breathe freely. Is the throat dry or not? Are their lips dry or not? And these are very specific symptoms that most people can answer very clearly and unequivocally. But then we get to the more difficult ones. How fatigued are you? Are you tired? I'm not at all tired. How did you sleep last night? Do you feel like working today? And one very important one at the bottom there, do you have a headache? Now, fortunately, it's normal not to have a headache. So most people answer, I do not have a headache. And then you get a distribution that is called a J distribution. In other words, most people are at this end. Most people, if you look at the frequency of people answering, would answer, I do not have a headache. Then there'll be a few who have a severe headache, and in between, an increasing number who don't have a severe headache. And that kind of result cannot be handled with statistics that assume a normal distribution. Think what a normal distribution would be. That would be that it would be normal to have quite a headache, and only a few people had no headache. So we don't use ordinary statistics. We use non-parametric statistics that don't assume a normal distribution to analyze these replies by the children. Now, I've taken some time to tell you about this because most classrooms are adjusted according to how people feel, all right? And we think that these visual analog scales give us a pretty good handle on how people respond when asked to how they feel. And we can then see whether the interventions that we made in terms of air quality, temperature, and dust in the air suspended dust do affect how people feel. And the short answer is they hardly notice the changes we've made. And I think that's very significant. We also measure performance. Now, this is something many researchers shy off doing because they think it's too difficult. I've been measuring performance since 1966, when I first came to Sweden and was asked to determine what were good conditions for work. It seemed to me to be obvious that the deciding bottom line factor, if you like, is what we pay people to do, or in the case of children, what they come to school to do, which is to learn things. They learn things by doing schoolwork. So in schools, we measure how well they do schoolwork, since doing schoolwork is how they learn. In offices, we measure what they're paid to do. In factories, we measure how many items they make and how many mistakes they make. It's not that complicated, but you often have to choose the office, the factory, the school, in order to be able to do it. I'm not saying it's easy to go into just any situation and measure performance, but performance is what should be measured because it's the bottom line. That's why we build schools so children can learn. We build factories so people can make things. We build offices so people can apply administrative ideas or preferably creative ideas. So in school, we developed 8 different tests to use in this experiment. We developed them with the children's class teachers so that they were at an appropriate level. And there's a reason for that. If you take a standard test off a shelf, and particularly if it is a test that's intended to diagnose whether children are normal or not, to sort the sheep into the goat, or from the goats, then it's deliberately designed to have huge inter-individual variance so that you get a score where the ones with dyslexia, for example, score very low. They're all collected around dyslexic, and the others score over here. It's a bimodal distribution. And when you have that kind of an underlying distribution, it results in a huge variance. It's deliberately huge because you're trying to separate the sheep from the goats. But in our case, we want a test where all the children can do it more or less the same, a single distribution around a common mean. That would be the ideal, because if we then make it more difficult by raising the temperature, then that will shift, and we can see a statistically significant effect of that intervention. Diagnostic tests are not suitable for this kind of work because they were devised for that other purpose, differentiating between different types of people. And yet, researchers continue to be browbeaten by psychologists who are used to that kind of work into using their diagnostic tests. And this increases the variance of their results, and they need huge experiments to be able to show any effects of the indoor environment. This was an insight I had right back in the 60s, And we use real work where people have trained to the plateau where they all work more or less as efficiently as each other. And the teacher was informing us exactly what level we should be at. You see, another problem with performance testing is that if the tests are too difficult, nobody can do them. If they're too easy, everybody can do them. So they cannot then be affected by the environmental conditions, because if nobody's doing it, they will go on being not able to do it. If everybody can do it, get 100%, they'll be up here. In between, there is a cumulative distribution of people who can do the test, and we want to place ourselves right in the middle, where, at the point of inflection, where this cumulative distribution between getting 0 on the test and getting 100% on the test is at its steepest, because then a small change in the difficulty of the test, brought about by changing the environmental conditions, gives the maximum effect on what we're measuring, the performance. So we had 4 language-based exercises. We won't call them tests, they're exercises, because they are representative of what the children normally do in school. Acoustic proofreading sounds very complicated, but it was just that they heard somebody reading up a text and they were looking at a transcript. And we had introduced discrepancies between the two, and they had to mark those discrepancies on their transcript. And so that they didn't just look at the other child and mark when they did, they all had different transcripts, so that the errors were in different places, so that there was no point in looking at anybody else's. We didn't tell them this, but we could then see if they were performing at random, because these discrepancies were introduced at random, and a child who was just copying somebody else would get a random score. So they had to be able to listen and read at the same time, and that's quite difficult for 10 to 12-year-olds. They're not used to doing it, and they were doing their best on this. On the other hand, the difficulty with this exercise is that the speed of working is determined by the reader. All we can measure are the errors they made, the errors they missed. Reading and comprehension is different. They read a text, and every 3 lines or so, there is a set of parentheses and 3 words. They're all correct in the immediate context. They're all grammatically correct, but only one is correct in the context of what they've read before. So if they haven't been paying attention to what they read, they can't answer correctly. They would have to go back, and that gives a time penalty in the sense that they are then losing time. They don't get as far in the text. We can then measure how far did they get in the text when we stop the exercise, usually after about 10 to 15 minutes. And we can see how many of these choice points were correctly answered. So we get speed and errors, or accuracy, if you like. Logical reasoning is a test that was developed in Cambridge by the Medical Research Council to measure how logically people can think. It was originally used to show effects of nitrogen narcosis on deep-sea divers. It's been used since then to show that doctors who've been up all night should not report for duty at 8 o'clock. They cannot think logically, as shown by this exercise. What happens is that there's a series of sentences which make a statement, such as A comes before B in AB, which is true, and you have to mark it true or false. It might then say B is preceded by A in BA, which is false, and so on. Each one very simple, but by the time you've answered 20 or 30 of them, you have to be thinking very clearly to be able to continue to answer correctly. Again, we get speed of working and errors. Most people reduce the speed of working in order to maintain an acceptable level of accuracy. So I always expected that this would be that the most sensitive would be speed of working, and that's actually what we find. Proofreading, that's just what you and I do every day when we've written something. We look through it to find errors. We had inserted errors into a text, and they simply had to mark them as they went through, but nothing difficult about that. The numerical tests consisted of simple subtraction, multiplication, comparison of long numbers into parallel columns to see if they were the same or different, and addition. And this is well-practiced work even for 10 to 12-year-olds. In fact, multiplication turned out to be too difficult for most adults when I used it on them. But the children can do it because they're used to doing it every day. We had to discard the results of a multiplication, and especially long division. That's why that doesn't appear, because we get a bimodal distribution, the ones who can remember the rules for long division and the ones who can't. People who've been doing it with calculators and computers for many, many years have often forgotten how to do long division, so we don't use that. The tasks were performed during the mathematics or the language lessons so that they were in the correct context. And they didn't take up the whole lesson. They were distributed over the course of a whole week at the discretion of the teacher, and they appeared to the children to be just simple exercises of the kind they do every day. We then simulated parents coming to the school for a parent-teacher meeting, for example, by bussing in a group of 20, 30 adults who were paid by us to be parents. They went into the classrooms after the children had gone, and they used the DTU scale of acceptability, which we use for everything from noise to air quality to draft and so on. Over the years, it's been refined to the point where we have thousands of responses on it, and from where people mark it in a small group, we can predict the percentage who would think it was unacceptable in a large group. So we get a lot more out of it than just it would appear. The scale goes from clearly not acceptable at the bottom to clearly acceptable at the top. And because many people, lazy, they don't want to make a decision, they would sit on the fence and put a mark in the middle, somewhere in between, we have a gap, and they're not allowed to put the mark in the gap. They have to choose between just not acceptable and just acceptable. So we get a binary decision. It is acceptable or it isn't acceptable. Now that gives us one bit of data per person, but we also measure the distance from one end so that we get a rating of acceptability. And it's that which enables us, by comparison with tens of thousands of previous responses, to get a relationship between the percentage dissatisfied and the average acceptability rating on this scale. So here you can imagine yourself going into a classroom and saying, oh, have they been working like this all day? And putting a mark clearly not acceptable, you know, or you come in and say, pretty good, like this place here. We have a very high ceiling here, so I don't know if it's ventilated, but the air's pretty good because the air I breathe out has gone up there somewhere. And I would put a mark fairly high up here, I think higher than that, for the air in this room. And I think most of you would. So we would probably agree that the air in this room was acceptable. Parents can make up their own minds about whether the conditions their children work under are acceptable. And they make a fuss if they think it isn't. Here, we were simply tapping into that. And these young people weren't parents, and they didn't have a personal interest. But on the other hand, they were totally blind to conditions. They didn't know which condition we had been running that day. To do an experiment like this, you need a lot of permission. It puts people off. And that's why in ASHRAE we insist that the necessary permissions have been obtained before we finalize a grant. We have to ensure that the parents are in agreement, that the school headmaster agrees, the school board, the teachers themselves, the local authority, in this case the Danish Ethics Review Board, and in the case of the schools we used in Sweden, 4 of them, the Swedish Ethics Review Board, because nowadays we have to make sure that the Ethics Review Board is on board. They have to say that it's reasonable to expose the children to these conditions. In the 60s, we just simply turned up the thermostat as we thought fit, and nobody had invented ethics review boards at that time. But nowadays, because there are so many researchers putting people through the hoop in quite unpleasant ways, the ethics review boards will not agree unless it's in the interests of the people concerned, if they are themselves patients, for example, being on which a cure is being tested. So it would be in their interests if it was acceptable. Or if the conditions are within what normally happens, then it would be foolish to object to us imposing conditions on children that normally occur. So we made sure that all the changes we made were for the better. So, and we also told them that the cooling equipment and the improvements that were made elsewhere, we put in bigger fans, for example, would be left in place. So everybody said, when can you start? We didn't have any problem getting permission. In fact, the Danish Ethics Review Board takes the view that we have a kind of a blanket approval because their time is valuable and they are using all their time to decide on whether people should be exposed to different new pharmaceuticals and other kinds of rather unpleasant experimental conditions. So if the engineers are simply trying to optimize conditions in a classroom, they say, you know, go ahead. Why haven't you been doing that before? The interventions always improve conditions. The interventions were for 1 week at a time in a balanced order of presentation. In other words, it went from good to bad or bad to good equally often. That means that we remove any effects of, for example, learning or familiarity that would have been in one simple direction. If the children are always better on the second time, then if you confound order with condition, then you will get the answer you want. So we balanced the order of presentation. And we used what's called a crossover design. One classroom with existing conditions and one on the same day and the same week with improved conditions, side by side. So that any changes in the weather, the sun, the clouds, the wind, and or any fire drill or hullabaloo that takes place outside the classroom will affect both of them equally. The crossover design like this is the gold standard for medical research, and I always use it if at all possible, even in field studies in heating and ventilation. Because if you do an experiment which can be criticized on the grounds that, well, some other factor could have affected what you were doing, you might as well not do it. The whole purpose of an experiment is to convince people that, to share your view, that there is an effect or is not an effect of the intervention you've made. So if there are other explanations, don't bother. There's no point in doing an experiment that is not convincing. A crossover design is very convincing. The ventilation system, as I said earlier, was modified to provide more air to one classroom at a time, actually 4 times as much as normal. And split cooling was installed in both, but operated in one classroom at a time. This is a typical design with current temperatures or cooled, and with current ventilation rate or raised, rebalanced ventilation rate. I remember the windows being open all the time, so if that was a major factor, that would be what determined it, and there wouldn't be much difference between high and low ventilation, what we call high and low, because we're blowing in more or less in the ventilation system. So we'll see what happened. This is what happened. The estimated effective litres per second per person, as estimated from the rate at which the CO2 level increased as the children came into the room, in the low and fluff high litre per second condition was this. Almost 10 litres per second per person in the high condition, that's this higher histogram here, and down around 5 in the low ventilation condition. You notice the small difference there is between with air conditioning and without. The green is the with air conditioning and the blue is without. That means that the ventilation was better in the no air conditioning. Why was that? Because they didn't open the windows as much. They opened the windows when it got too hot. So they got slightly more air, but as you can see, it didn't make a lot of difference. So we had a clear difference between high and low ventilation. And for those of you who are familiar with the numbers, 10 litres per second per person is more than is recommended in places like the United States, but it's about what is recommended as a minimum in Scandinavia. We recommend it, but as you see, we don't live up to that. 5 is what they were getting when those fans had been reduced in speed in order to save energy. And that's generally regarded as too little. Not a lot too little, but too little. You see, it led to mean classroom CO2 levels that were around 1,000 in the low ventilation condition. High CO2 condition, I was going to say. In the low ventilation condition, we were getting up to about 1,000. And in the high condition, we were keeping them down to about 800. Now let's look at the peak values. These were the mean values. The peak values were getting up to 1200. This is the average peak across a dozen experiments, across scores of sessions of days, because each session is 5 days, plus another 5 in the other condition, okay? So these are averages of the peak condition. And as you can see here, when we were controlling the ventilation here, even the peak didn't get above 800. Now, if you showed this average condition to a school inspector, he would say, okay, go for it, this is acceptable, because 1000 ppm is considered acceptable. Many experiments on air quality and ventilation rate are done at 2,000 to 3,000 ppm, the levels that occur exceptionally in classrooms. They occur a lot in submarines, for example. Researchers believe that you have to go up to these extreme conditions to show that CO2 has an effect, has a negative effect. We didn't think that would be very interesting, so we wanted to work here around what it is and should be, okay? So most researchers, before we did this experiment, would have said, you're never going to get an effect on performance, which is so difficult to measure, of changing from 1200 to 800, or changing from 1000 to 800 on average. Remember, there were no restrictions on normal daily activities, no changes in the class schedules, the doors and windows could be opened freely, and there was no contact between researchers and children, no white coats or stopwatches visible anywhere. Now, we'll look first at the reduced classroom temperatures. 2 independent experiments series were done in August and September. That's when it starts getting warm after the summer holidays. Of course, it's warmer during the summer holidays, but we couldn't get hold of the children then. In the first experiment, the temperature was reduced from 23.5 to 20 at 2 ventilation rates. In the second experiment, the temperature was reduced from 25 to 21 with the mechanical ventilation switched off. And other parameters of classroom indoor environmental quality remained unchanged. Now again, if you had asked, before this 1257 series of experiments was done, if you had asked researchers if they thought we would get an effect on performance of making these fiddling small changes within what's known as the comfort zone, between 20 and 25, if they would affect performance, they'd have said, no, you're wasting your time, you're wasting ASHRAE's money. Particularly since it didn't get hot till later in the day. You can see here a typical time course of classroom temperature in the 2 classrooms. We're controlling it because we can switch on and off the cooling. We're controlling it fairly well around 20, but it just meanders up depending on how often the children are out in a break or in the classroom, whether the sun is shining through the windows or not. And as the sun comes around to the south, it goes up around 12 o'clock to the maximum level and only slowly down from that. So again, you know, it was pretty long odds that we would get an effect of temperature on school performance, people thought. Particularly when you look at the children's perception of temperature. This is on the scale from too cold to too hot. At the low temperature, 20, they were right in the middle. Now remember that, because people often say 20 degrees is far too cold for schools. You know, it has to be warmer than that. And in the high temperature, it didn't bother them. It was statistically significant. That P less than 0.001 means that if we did the experiment 1,000 times, we still wouldn't get such an extreme difference in perception between the 2 conditions. That is the result of non-parametric statistical calculations based on their markings of the scales. So, depending on the measurements, depending on the perceptions, we were making small changes in the temperature. I think you'll agree. So how did it affect them? Yeah, and those of you who like the PMV that my former colleague P.O. Fanger introduced, we were at 0.7 or 0. So it was dead on what we think it should be for children, and they agreed. And the PMV was 0.7, which is well within what people regard as a comfortable thermal condition. Remember that in Japan, in America, they don't start the air conditioning these days until it gets above 27. in order to save energy. But this is what happened to schoolwork when we express each exercise as a percentage of their performance on both conditions, so that we can put all the different exercises on the same graph. We get a regression that accounts for 68% of the variance. The R2 is the square of the correlation coefficient, and that represents the proportion of the variance that we can account for with temperature. And you can see that from 20 to 26 there is quite a decrease in performance. Well, 25, we didn't go above 25. And how big is that effect? Each degree of temperature that we reduced the classroom air by gave a 3.5% better performance. Okay? Better performance as the temperature decreased up here. Now, that doesn't sound a lot, but remember, the temperature has changed by a lot more than a degree. You saw that in the graph of what happened during the day under normal conditions without cooling. And in 1967, it's a long time ago now, nearly 50 years, when I did my first experiments by simply turning up the thermostats in the teacher training college in Malmö in the south of Sweden, we raised the classroom temperature in one condition to 30 and we kept it at 20 in the other. And I reported at that time, in 1967, that it reduced most types of schoolwork performance by 30%, by up to 30%. And for 40 years, this was widely believed to be an overestimate. People said, okay, I can believe 4, but not 40. But the present results that I've just shown you in the previous slide confirm the size of the thermal effect that we first reported in 1967. Ingrid Holmgren and I reported that effect of 30 degrees contra 20. If we apply a 10-degree change like as we happened in 1967 to our present results, we would predict 35% less schoolwork would be done during this session, and that's what we observed in ASHRAE 1257. A 30% effect of performance. So 2 experiments done in different places, different countries, 40 years apart, show exactly the same effect on the performance of schoolwork. Children do not work as well in slightly warm classrooms, and we ought not to expect them to do so. Now let's look at the increased outdoor air supply rate. We've got better at doing this kind of work over the 40 years. I wouldn't have dared to tackle air quality in the 60s, but now we can both control it and measure its effects much more effectively. We did 3 independent field intervention experiments with 100% outdoor air supplied through new filters. In one, we increased the outdoor air supply rate from 3.4 to 9.5, the next from 3 to 6.5, and the next from 5 to 9.5, with and without cooling. Remember that we don't, on our own, control these conditions as we would in a laboratory. We would have had absolutely 3 or 4 and absolutely 10 in a climate chamber, because we would be controlling every litre of fresh air that came in. But in the classroom, we don't. They can open and close the windows and doors, and they go in and out, and those are the things that affect the amount of fresh air coming into the classroom. So we were quite pleased that we got such a big difference, as you've seen previously, in CO2 levels between conditions. Between conditions, there was a big systematic difference. But at any given time, the CO2 levels were all over the place. This is a typical daily record of the CO2 level in a classroom, which is meant to be with low outdoor air supply rate. That's the yellow one, and with the red one, and with higher outdoor air supply rate, that's the yellow one. You can see that they even cross over at times. So again, people would say, well, with that kind of lack of control of air quality, you're never going to get a difference between those conditions, because CO2 is all over the place. But it was systematically higher at all points in time when we were supplying more outdoor air. It's just that there was a huge variance in the independent variable, as it's called. So how did we find, and how could we expect to find an effect on the dependent variable, which is the performance? Let's look first at how the children judged it. In the low ventilation, they could have marked it right down at poor air, but they were halfway between poor and so-so. Okay? They were dissatisfied, but on average, but not all that dissatisfied because it was normal. That's what they were used to. When we increased the outdoor air supply rate, it was better, systematically better, significantly, statistically, significantly better. But they didn't even come up to the middle. So they weren't saying, wow, you know, at the top end of the scale, which they could have done. They were, on average, just below good air. So what did the parents, the untrained panel, tell us on their DTU scale of acceptability? In the low ventilation, the red column shows that 35% thought the air was unacceptable. And that's the normal condition. Well, if they thought that, if the parents thought that, they should have said something about it, shouldn't they? But they didn't. Those are the normal conditions in that school. 35% of people coming in from outside say, I wouldn't work in this, it's unacceptable. When we increased the outdoor air supply rate, that percentage fell to just below 20. Again, statistically significant difference in perception. But remember, they were not experiencing these ups and downs. They were coming in at a particular point in time. But there will have been a fair variance, depending on how often the children had been out to play during the day and what the wind speed and direction was and how many windows were open. So the parents noticed, the children noticed, but they're not huge differences. It's not everything good, everything bad. But was performance affected? Well, don't try and take in all of this, but the stars show that there was a statistically significant difference between two conditions in these exercises. Virtually all of the exercises showed a statistically significant effect of air quality. And this is what it looks like on a dose-response curve, where we plot percentage change in performance, percentage performance, against the outdoor air supply rate. There's a clear negatively accelerated trend, which has been matched as well as we can to account for 60% of the variance. Highly significant, of course. And you can see that up around 10 litres per second, we starting to level off, but it's still on the way up. It will be very interesting to see what happens between 10 and 20. Do we get more for spending that extra fresh air, or don't we? But in this area, between 3 and 10, we seem to be getting a fair bit. Well, how much is it in real terms? Doubling the ventilation rate produced 14.5% higher performance. That's a lot. So classroom air quality matters. Windows are often not opened for various reasons. Outdoor air supply rates are often low, again, for various reasons, some of them economic. CO2 levels are often above 1,000, and I'll show you how often in a moment. Increasing the air supply rate from 2.5 to 5 and again to 10, doubling it twice, would improve performance of schoolwork by 29%, 2 times 14.5. So we're getting up to the kind of effects on performance that you get by allowing the temperature to rise to 30 degrees. Poor air quality is a major disadvantage for children and especially for slow workers because the effects were almost all on rate of working. There were a few effects on accuracy, but most of the effects were on performance. Children have a choice. They can slow down to maintain an acceptable level of accuracy, or they can just maintain what they see as an acceptable speed, and then it should show on the accuracy, but that doesn't happen. What they do, in most cases, in our experience, is just as adults do. They slow down in order to maintain acceptable accuracy. Now, I'll go to that in a minute, but I just want to let you think about this for a moment. If temperature and air quality are both having an effect on performance, why don't we see differences between summer and winter? Why aren't these effects obvious to teachers and parents and children? The reason is that in winter, the windows are closed because it's too cold outside and too windy and drafty, so the children work is depressed by the air quality. They're not getting enough fresh air. In the summer, it's okay to open the window, so the air quality is all right, but it allows the classroom to warm up when it's warm outside, so their performance is depressed by the temperature. So the teachers don't notice any difference between the two seasons. It's only in spring and autumn when, I'm sure you remember as adults, that's when you felt like working. In spring and autumn, it was fresh outside, and the air quality is good. That's when you felt you could really tackle the year's work in October. I know I felt like that when I went up to university. And I think it's an effect of the environment. And it's a tragic result of poor engineering that children are working 30% below their capacity all the time for different reasons. Now, just how bad is it? In October 2009, we did what was called a mass experiment. We sent out equipment for measuring CO2 to 1,663 classrooms all over Scandinavia, in Denmark, Sweden, and Norway. And they measured at a given point in time what was the CO2 level in their classroom and sent us the results. And as you can see, well, perhaps you can see, I'll be making this clearer in a moment, it was divided up into natural, exhaust only, and balanced ventilation. And in the natural ventilation, which is the most common in Denmark, in Germany, and other temperate countries, 1,000 ppm was exceeded in 69% of those classrooms. 69%. In exhaust only, in Denmark, 50%. In balanced ventilation, still 37%. There's no real excuse for that, because once you've paid for balanced ventilation, it should be providing enough outdoor air to get below 1,000. But in 37% of cases, it wasn't. And it was even getting up to 2,000 ppm in this measurement in quite a few classrooms, up to 30% in the naturally ventilated Danish classrooms. Now, this is just simply unacceptable. Classrooms in Denmark with natural ventilation only, there was 69% above 1,000 ppm. In Sweden, 47%. In Norway, 48%. This probably reflects the difference in outdoor temperature more than anything. And if we take all 1,663 Scandinavian classrooms together, then we have 56% of all children, our best estimate, are exposed to more than 1,000 ppm. In Denmark, 20% exposed to above 2,000. And much better figures for Sweden and Norway, because it's so cold in the winter in large parts of Norway and Sweden that they have gone to proper ventilation, because they know they can't open the windows. But in most of Europe, they rely on window opening to maintain, in other words, natural ventilation, to maintain good air quality. We then, because these were measurements made by amateur children, we then went to actual measurements in 100 classrooms in Denmark. It was a structured representative sample. So the number of naturally ventilated classrooms was in proportion to the number of exhaust only and the number of fully ventilated classrooms. And we recorded CO2 throughout school hours. When I say we, DTU, 2 of our PhD students did this during 2 weeks in November. The outdoor temperature at that time was between 0 and 15 degrees. They measured all the time whether the children were present or not. And the proportion with an average CO2 level above 1,000 was 66%, very close to what we had got from the mass experiment. 66% of Danish children are being exposed to CO2 levels above 1,000. And I've just shown you from the ASHRAE 1257 experiment what that's doing to their schoolwork. We were comparing 1,000 with 800 ppm. In an intervention experiment on adults in a call center, we changed the filters and we produced a great improvement in performance. They worked better, corresponding to about 10% when we gave them a clean filter compared to a dirty one, because dirty filters are a source of pollution downstream. Engineers see dirty filters simply as blocking the airflow, so they increase the fan pressure and they change the filters when that's uneconomic. I see dirty filters as a source of pollution, especially when you have recirculation. In these schools, we saw no consistent effects on perceptions, symptoms, or perceived air quality when a used filter was replaced with a new one. And I forgot to mention that you didn't see any effects on symptoms, and that's because there weren't any to speak of. The children hardly noticed, in terms of their eyes, ears, nose, headache, and so on, that we had changed the conditions. What it affected was their work. We think that the reason we got no effect on speed or errors by changing the filter in this experiment, you can see here, no difference, no convincing difference, no significant difference. And this differs from our office findings, but there was very little dust retained in the used supply air filter. It's a clean area, as I said at the beginning. And the supply air was 100% outdoor air, so all the dust originated outdoors. The dust in those filters was outdoor dust. And this apparently doesn't have any negative effect on children. In the adult experiment, a lot of the air was being recirculated, so most of the dust in the filters was coming from indoors, and that did have an effect on the adults' work. Those electrostatic air cleaners, let's look at what effect they had. 2 independent experiments were done in January and March, April in 1 Danish and 4 Swedish schools. That's a lot of experiments. The concentration of particles in classrooms was considerably reduced when electrostatic air cleaners were in operation. The placebo units are those where the fan's running, recirculating the air, but there's no voltage on the deposition plate. The blue are the air, when the air cleaners are operating as designed. And you can see that particularly in the small particle range, we are reducing the number of particles per cubic centimeter. And even up here, there's quite an effect. So we're trapping most of the particles. But electrostatic filters trap fine particles more easily than big ones, because they have a bigger, a faster rate of turning in the electrostatic field that is introduced. These are the 5 classrooms, just rank ordered from the poorly ventilated ones at this end, the Danish ones, to the 4 Swedish ones here. And again, the red is in the placebo condition, where we're not removing particles, and the blue is where we are. So you can see that we got quite a significant measurable effect on reducing the number of particles per cubic centimeter. You'd think you noticed that. But operating electrostatic air cleaners had no effects on performance, not on speed, not on errors. We'd only have to do 2 experiments to get the differences here, so they are entirely due to chance. Our conclusions on filters and airborne particles are that electrostatic air cleaners do reduce the concentration of airborne particles, but they have no effect on schoolwork. Installing a new filter in the outdoor air supply flow had no effects on schoolwork either. But reducing the airborne particle concentration may reduce the long-term effects of indoor air quality on health. We weren't measuring that. And of course, if you have people with allergies or asthma or pollen allergy particularly, filtering is extremely important for them. So we're not saying that you should not install filters, only that its effects will be on health and not on performance. It's not a cheap way to stop bringing in outdoor air. So our main conclusions in ASHRAE 1257 are that reducing even slightly warm classroom temperatures eliminated thermal discomfort and improved children's performance. Increasing outdoor air supply rate improved classroom air quality and children's performance. And schoolwork was performed faster with no increase in errors in both cases. I'll just mention, since I'm speaking English today, a series of experiments done by one of our former colleagues, Bako Biru, and his British colleagues in the United Kingdom in 2012. That is long after 1257 had been published. That is published in Building and Environment, volume 48. They installed equipment out in the schoolyard and brought ducts in through the windows because they chose to use classrooms that did not have existing ventilation, and that made their job much more difficult than ours. But they succeeded in changing the air supply rate from 1, that's very, very little, litre per second per person, to 8, which is getting up to what we had in 16 classrooms. So you imagine the work to do that, taking the equipment around like a circus to different schools and rigging up the ducts and making sure that you don't change the air temperature, because those ducts have to be insulated against the outdoor temperature. It was a very difficult experiment to do. But they made one mistake. They used diagnostic tests and not schoolwork. And diagnostic tests are not sensitive to the environment for reasons that I have explained earlier in this lecture. They did, however, find a significant improvement at 8 litres per second compared to that extreme condition of 1, which we didn't even go to. Test performance in their experiment was improved by ventilation by between 2 and 15%. Still a convincing reason to ventilate, but I think not quite as convincing as if they had done the experiments blind to the children with real schoolwork and at more realistic levels of ventilation. Well, that's what I have to say. That's what I have time to say today. I have a lot more to say, but I'm not going to be able to say it. So I'll end this lecture now. Thank you for listening. Do we have any questions sent in from the virtual participants? No? I can go offline.
There was one question, David, that I got. And that was to do with, you mentioned at the start of the lecture, something to do with the electrostatic cleaners. And you said it was a new technology that was used there. Is that still considered to be a new technology, the electrostatic cleaners that you used then, or has the technology since moved on?
I'm not aware of them being commercialized to any extent. We took the idea from Professor Turek at the Royal Technological University in Stockholm, here in Stockholm. Professor Turek, right back in the 70s, as I remember, was a Hungarian working in Sweden who had devised this way of removing particles, and with these advantages that it's very little pressure difference and a huge deposition area that can easily and cheaply be changed. And we simply rigged up prototypes. We weren't able to buy any. What's happened since then, I can't say, but I don't think that kind of electrostatic ventilation has, filtration has yet penetrated the market to any extent.